So welcome back learners, and this is going to be the last session on our journey on computational process design. Today we are going to learn about ecosystems in sustainability assessment and how it is being used for integrated design. We would learn concepts like industrial symbiosis, we would learn concepts like circular economy, etc. on the go. And this is going to be, as I told, this is going to be our last session in this particular course. So before we move ahead, again, we can see this is the reference list, and this part of the topic is mostly coming from the reference 5 by Bhavigar Bakshi, Sustainable Engineering Principles and Practice, Cambridge University Press, and you may feel free to refer the above reference textbook. So maybe let us just do a quick recap on what all things we were doing. So, okay, so we were talking about life cycle assessment, which is a methodology that is used to evaluate environmental impacts of processes or products across the entire lifespan, which we typically call from point of extraction to the point of disposal. And to do that, we will have to do certain energy analysis, which is a critical component to LCA, which quantifies the consumption and transformation of various forms of energy. And then we looked at the concept called exergy. Exergy is what we call it as the useful or the available energy that determines that can perform work within a system, which is emphasizing on the quality of the energy relative to the surrounding environment. Then we talked about a concept called transformity, where in LCA, so it indicates the energy quantity reflecting the amount of solar energy required to produce a unit of energy. Higher the transformative values indicate the more significant energy transformation and higher energy quality. Then we looked at a concept called emergy. Emergy is a comprehensive approach that accounts for all energy input, both direct and indirect, which is converted into the solar energy equivalence. Fine. And we talked about uncertainty quantification in LCA. There are parametric uncertainties which relates to the relates to the variability in the data. Then scenario uncertainty, which is coming from the system boundaries and functional unit as part of different assumptions. And the next is model uncertainty, which arises from the simplification that you need to make a model of a complex system to a simple system. Then how to improvise the LCA reliability? There are statistical techniques such as sensitivity analysis, scenario simulations, and so on and so forth. And as a summary, a nuanced understanding and management of these uncertainties, of course, ensure or helpful for more transparent LCA results. So now let's go to the topic of the day and how to compute the what we call as the life cycle impact assessment. Okay, and if you look at, there are the inventory. So we have a lot of things which we call it as the inventory, that includes gases like CO2, SO2, NOx, SOx, benzene, of course, minerals like nitrogen, petrol, potash, crude oil, iron, gas, land, water, everything. Fine, and we would like to attribute them what we call it as the midpoint category, which essentially means that, for instance, CO2 and HCFCs would result in climate change. Fine, HCFCs of course also result in ozone depletion. SO2, NOx, etc. would result in human toxicity. Some of components would result in acidification. Then photochemical ozone formation, eutrophication, water use, resource use, and land use. So all of these components would result in one of this uh, classification, which we call it as a midpoint category. So your inventory due to all of these inputs would result in some of these effects that are tangible, which again we could just further summarize. See, for instance, climate change, okay, ozone depletion could result in human health. Okay, of course, climate change can hamper ecosystems, acidification can hamper human health, it can hamper ecosystem. So All these bigger categories could be again summarized into three categories, which are human health, ecosystem, and resources, which we will be able to summarize as single point indicator. From the starting, from the inventory, you would reach to a midpoint category. Of course, then uh, it would result in certain areas of protection that we can do, and eventually it would result in what we call as the endpoint indicator, which would be a single quantity that we wanted to evaluate all these effects. And how are these categories? So, for instance, climate change. For instance, climate change and the causes are typically the release of greenhouse gases and CO2, CH4N2, and CFCs, and eventually it is computed as kilogram of CO2 equivalent. Similarly, ozone depletion potential. It is the emission of gases that causes loss of stratospheric ozone, such as chlorofluorocarbons and hydrochlorofluorocarbons, and this is typically computed as kilogram of CFC11 or equivalent. And photochemical smoke formation, the reaction between NOx and volatile organic compounds in the presence of sunlight to form ground level ozone. So this is typically computed as kilogram of O3 equivalent. And the next is human health pollutants. This is computed as the pollutants such as particulate matter uh, and other various toxics. These include hundreds of chemical compounds. This is computed as kilogram of 1,4-dichlorobenzene or equivalent. The same for ecotoxicity, the pollutants that are toxic to the ecosystem, including various chemicals. This is also computed as equivalent of 1,4-dichlorobenzene. The next is acidification, addition of hydrogen ions to the local environment, which is caused by emissions such as NOx and SOx and ammonia and so on and so forth. This is computed as kilogram of SO2 equivalent. Next is eutrophication, which is the presence of excessive nutrients such as nitrogen and phosphorus compounds. This is kilogram of nitrogen equivalent. And land use, of course, the area of the land use, this is of kilogram of N equivalent. And eventually resource depletion, the fossil fuel which is for mineral use, which is computed as of which is typically computed as antimony equivalent. So these are the corresponding classification and the corresponding conversion. So now let's move further forward. So how to characterize the common units? So typically when we have this inventory data is available, they are classified into the same category but are multiplied by the corresponding characterization factor to represent all the flows in the common unit of the category. For instance, HI, if HI is the total impact factor for a category I, it is computed as a summation of all J's, and psi ij Rj. So, and what is Rj is the mass of the inventory flow of J, and psi ij is the characterization factor for the impact category I and flow J. So this typically represent the chemicals classified in the same group in terms of common unit to permit addition. This resulting thereby resulting the impact category, which we call it as the midpoint impact category. So for instance, if you see CO2, fine, uh, and CO, NOx, SOx, silver, so and so this is one such an example. Okay, so you could all find out it's what we call it as the global warming potential, ozone depletion potential, human toxicity, acidification potential, and the resource depletion. And all of this would have, for certain quantity, you shall be able to identify the corresponding factors, and this is how you could add up. For instance, CO2 for a quantity of 1.792 kg is equivalent to 1 greenhouse gas potential. Fine. But CO on the other hand, 6.7 10 power E minus 4 equivalent to 0.012 times human toxicity, and so on and so forth. So this is how to typically uh, compute. So now how do we do an integrated assessment that includes humans? So till now we are all talking about ecosystems and its calculation. Yes. So now how do we compute a case wherein human and ecosystem in environmental assessment. So let's consider various scenarios. Okay, the scenario one is the synergy between human and the natural systems. So what is the role here? So enhancing the biodiversity through agricultural practices that mimic natural ecosystems, supporting both food production and wildlife conservation. This can enhance the synergy between human and natural system. Urban planning that incorporate green space, promoting mental health benefit for residents and habitats for urban wildlife. Implementing a renewable energy solution that do not only reduce the carbon emissions but also conserve the water and soil health. So this all would helpful in for increasing the synergy between human and natural systems. So now let's look at the ecological footprints in LCA. So for quantifying the environmental impacts of products and services by assessing their ecological impact, including the land and water use, carbon emissions, and waste generation, we typically do the compute the ecological footprints. Okay, and what? So what is its implication? Adoption of more sustainable consumption patterns and production techniques reduce the ecological footprints, fostering the balance between human needs and environmental capacity. Incorporating ecological footprint findings in LCA to inform policy and consumer choices, aiming for sustainability goals and reduced environmental impacts. So now let's look at ecosystem services. So we have now started with human and natural systems. Now you included the ecological footprints. Now let's also include the third component, which is the ecosystem services. So, in ecosystem, what are we trying to do here? In this context, we are trying to recognize the value of ecosystem services such as air and water purification, climate regulation, and pollination in LCA framework to highlight the contribution of human well-being and economic activities. Integrating ecosystem services valuation into LCA typically, it gets in sustainable resources management, conservation strategies, and enhances the resilience of ecosystems. Okay, so and further, the developing methodologies in LCA to accurately capture the benefits and trade-off of ecosystem services, thereby supporting the decision-making process that seeks to maintain okay seek the natural capital. So now let's look at the cases. Okay, so how do we evaluate this technological synergy? So if you have, so there are multiple steps involved. First of all is, so you have to set up the goals. So then you have to find out the alternatives, identify the opportunities, then look at the technological systems, scope of ecological systems, and ecological service shed. Service shed is the area in which we do what you call our analysis. For instance, if you are looking for conservation, watershed is the service shed. Okay, inventory analysis, the inventory of technological system, inventory of ecological system, in allocation of ecosystem services between users, because ecosystem services are typically available as a general service. So you have to actually allocate that between the users, and you finally compute the impact assessment by calculating the local and service shared sustainability metrics based on what we call it as the ecosystem service overshoot. Okay. The use of LCIA, which is life cycle impact assessment, to quantify the impact of excess flows that are not mitigated by the ecosystem. These are the steps. And how do we do it? Every time it is a feedback process. You have to interpret the results and for improvement. Okay, encourage the technological changes that reduce the environmental impact. Okay, encourage the technological changes and ecosystem restoration to enhance the supply of ecosystems services and develop ecological synergy. So these such an integrated system is what you typically need to work with or design with. So now the next question is, how do we allocate this ecosystem services? So you have a larger service shed. Okay, and there may be properties. Okay, so for instance, So let's see how this is being done. So allocation is necessary for local and at the service shared scale. So this is locally and also in the larger service shared scales. At local scale, e- ecosystem services are assigned to the activities that demands them, and especially if the services come from the land owned by the activity. And the next point is ecosystem services from publicly owned land are for the users within the service shed and must be distributed. So see, you can't kind of claim that this is only for my objective, but everywhere. So see, if the ECs are coming from a publicly owned property and it has to be kind of distributed across all the stakeholders. And how do we do this allocation? The process can be of course subjective, and you can consider multiple factors. The criteria may include quantity of the years used, economic value of the activities, and the number of people employed or affected by those activities. And how can we compute the weighting factor? Okay, one possibility is WIK, weighting factor. WIK is DIK divided by sigma DIK, and DIK is the demand of the ith activity for the kth ecosystem services, and that's how you compute the weight uh, of the ith activity for the kth ecosystem services. So now let us see a small example. How do we do such calculations? So look at this particular problem. An urban area consists of three localities and a public biodiversity conservation area. The emission of NOx in the each locality is 50,000 ton per year, 5,000 tons per year, 1,000 tons per year, and 3,000 tons per year. The areas of each locality are 2 kilometer square, 3 kilometer square, 4 kilometer square, and their capacities to sequester NOx are 2000 ton per year, 1200 tons per year, and 1500 tons per year. Okay, comma respectively. Then the NOx capture capacity of the public area is 20,000 tons per year, and its area is 2.5 kilometer square. The emissions from this area is negligible, so allocate the capacity of the public area to three localities in proportion to the demand in the local area. So let's look at the problem. So we see that the sequestering capacity of 20,000 ton per year we have to allocate into the basically based on the demand of NOx. So look at the first case, SL1A. So you have 5,000 divided by 5,000 plus 1,000 plus 3,000, which is a fraction times 20,000, which would be okay 11,000 1111.1 ton per year. Other cases, of course, you consider the locality B, which you have 1,000 would be in the denominator, 1,000 divided by 5,000 plus 1,000 plus 3,000 into 20,000, that will be approximately computed like this. And similarly SL3A, so again 3,000 divided by 5,000 plus 1,000 plus 3,000 into 20,000, that would be 6,666. So now the similarly another way is to do an allocation based on the land area in the allocated supply among the three localities. So you have 2 kilometer square, 3 kilometer square, and 4 kilometer square. So 2 divided 2 plus 3 plus 4 times 20,000, that would be 4,444.4. And for the case B, 3 divided by 2 plus 3 plus 4 times 20,000, that would be 6,666.7. And the case L3, which is the case C, which is 4 divided by 2 plus 3 plus 4 times 20,000, which is 8,888. So what are we trying to see here? Such a solution show how the public area capacity to sequester NOx is distributed among three localities based on their respective emissions and demand of the land area, highlighting the method of allocating the environmental services. So now kind of let us devise a computational structure to kind of include the ecosystem services. You would see that this is an extension where we integrate the technological and ecological systems to assess the sustainability. We have done this in the as a part in the one of the earlier lecture where we kind of only counted the technological uh, effect. So now we will also bring in the ecological system. So before we move ahead, let's define AIJ as the flow of the jth economic good or services to or from the process. Dij is the interaction between the technological and ecological system, and Sj is the capacity of the jth ecosystem to provide ith flow. So let's look at the first two cases. So for instance, the balance equation across economic flow, it would be A11 M1 minus A12 A12 M2, which is F1, and similarly A21 M1 minus, of course, and A22 M2 would be equal to F2. And this, of course, we can write as a compact vector matrix form. AM is equal to F, where A is equal to the matrix that comprises A11 minus A12, A21 and A22, which is, of course, we call it as the technology matrix. We have done this earlier. And M is the scaling factor or multiplier, which is the vector of M1 and M2, and F1 of 2 is the final demand. Similarly, we could also bring in the environmental flow here. So in the similar fashion, it would be written as, so dm is equal to r, where d would be in this context minus d11 minus d12 d21 and d22, which is the what we call it as the environmental intervention matrix. Fine. So now let us see the next step. How do we integrate the ecosystem? So we can see here we have an ecosystem in each of this case, E1 and E2. Fine. And so when we include the ecosystems, so it would be, your matrix would be expanded A1 M1 A11 M1 minus A12 M2 minus C11 M1 E plus C12 M2 E, which is of course equal to F1, and similarly minus A21 M1 plus A22 M2 minus C21 M1 E, which is equal to F1. So what is C here, which is an additional term, which is represent the flow of an economic activity from ith technological system to the jth ecological system. So these coefficients represent the transaction typically between the technological system and the ecological system by means of economics flows. So again, so we could add the environmental consideration. So minus D11 M1 minus D12 M2 plus S11 M1 E minus S12 M2 E F1 E. So D21 M1 plus D22 M2 minus S21 M1 E minus S22 M2 E, which is F2 E. So here we have additional term M1 MIE, which is of course M1 could be M1 E, M2 E, M3 E, and so on and so forth. This is the scaling factor for the ith ecosystem, and FIE is the final demand from the ecosystems, or the net flow is to the net flow to the society of the ith flow. So now we could now integrate this together and write in a vector matrix form. So we can have a block matrix that contains A, D, which was the previous cases. So we add two more blocks of C and S, and we have M. In addition to M, now we have ME, and then in addition to F, we have FE. So C is the environmental management matrix, S is the ecosystem matrix, and this is now integrating all the features. And if you want to simply isolate the technological matrix, that would be ATE MTE, which is of course equal to FTE, and the final demand of FE may be multiplied by the characterization matrix phi if you want to assess the impact of the emissions. So this we have done earlier. HE is equal to phi times FE. So let's now try to solve a problem in this direction. So look at this particular case. So we have four figures of fuel production, electricity generation, and of course the associated ecosystems in line with that. Okay, and what we see here is the life cycle of fuel production and power generation and the surrounding ecosystem. The fuel production facility owns the land whose soil sequesters 100 kilogram of CO2. Find the fuel production facility also has, so this electricity generation facility also has a land that actually sequester 500 kilogram of CO2 and 80 kilogram of SO2. So now how to write the balance equations for this entire system. So let's proceed it as in the similar lines. The balance equations for only technology would be 20 liters minus 2. So 20 M1 minus 2 M2 is equal to F1. Fine. Next is the electricity is only output here. So 10 M2 is equal to F2. This would now aggregate together to form a matrix of 20 minus 2 0 10. The balance equations for ecosystems, okay. So of course would be now, so you have CO2 emissions, SO2 emissions, CO2 emissions and SO2 emissions. So it would be 10 M1, fine. So 10 M1 plus, okay, M2 minus 100 ME1 minus 500 M2 M1 M2E, which is equal to F1E. So you have sequestering 100 and 500. So first is we are only writing the CO2 balance generated and sequestered. So now doing the same thing for the case 2, which would be 2 M1 plus 0.1 M2 minus 80 M2E, which is F2E. So you can see over here. So if you go ahead, 2 plus 0.1, again in this case there is no sequestration, but in this case it is a kind of 80. So now if you could integrate these part only together, it would be 10, 1, 2 and 0.1, fine. So now we can integrate the S matrix, fine. It would be 100 minus 100 minus 500 and 0 and minus 80. So now how to integrate all of them together? So it would be like a nice block matrix system. Since there is no economic input to the ecosystems, the management matrix of C, which is recorded here, is 0. So there is no economic input to the ecosystem. This is 0. So that would be like 0 0 0 0. Thus the technological matrix ATE is of this large structure. So now let's talk about the concept of time value of money. So now that we have to monetize everything, so now we have computed this in terms of the flow. Now let us calculate this everything in terms of the profit, for which we'll have to look at what we call as the time value of money, which I think you have also covered little bit earlier, but then this is like a recap. So designing sustainable process and product requires balancing environmental, social and economic benefit. So what we have, so you have the revenue earned from the selling the products, and there would be depreciation for the capital assets, and of course there would be gross profit, which we call it as PG, which is computed as the difference between the the revenue and the operational cost, and the net profit, the profit after taxes, or whatever we call it as the net profit, is be 1 minus fee times PG minus D, where fee is the tax rate. Okay, so it's for a present value of P, the annual interest rate, or the future value after n years, with simple interest rate would be 1 plus F is equal to 1 plus F is equal to P times 1 plus Rn. And if it is compound interest, it would be F is equal to P times 1 plus R power n. And if the interest is compounded at a rate which is other than annual, it would be F is equal to P times 1 plus R by n times power to the power m times n. Fine. And so now we can of course do this if the present value of a situation with the present value of a situation in which the operating cost of A has incurred at the end of each year, which would be computed as 1 minus 1 plus R power minus n divided by R times A, where A is the operating cost, and if the payments are made in M periods, it would be, so your P would be 1 minus 1 plus R by M power minus mn divided by r by m times a. So now let us take a look at it. So the total capital investment that is needed for certain for process is 20 million. Out of this, 8 million depreciates at the rate of 2% per year. The expected revenue per year is $1 million, and the total cost before the depreciation is okay 800,000. Calculate the gross and net profit of this process with if the tax rate is 20%. So your PG would be 1 times 10 16 power 6 minus 8 into 10 power 5, which is of course this sorry which is 2 into 10 power 5 dollar per year, and the PN would be 1 minus 0.2 uh, 1 minus 0.2, the tax rate is 20%. 2 into 10 power 5 minus 0.02 into 8 into 10 power 6, so which is like a depreciation factor of 0.02, which is 2%. It would be $32,000 per year. And in problem 2, again look at the case. A particular car costs $20,000, fuel, insurance, and the maintenance cost is $1,800 per dollar per year. Assuming that the operating costs are paid at the beginning of each year, what is the total cost of the car over a 5-year period in terms of present dollars? Consider the annual interest to be 8%. So again, it would be P. So you have your initial cost 20,000 plus 1 minus 1 plus 0.08 power minus 5, which is corresponding to the 5-year thing, divided by 0.08, which is annual interest. 1.08 comes from 1 plus 0.08 and into 1800 is the maintenance cost. So it would comes out to be 27,187. So now let's look at some of the profitability metrics so that we can quantify the entire operation. So you have return of investment, which is a measure of the profitability of the investment as a percentage. It is typically computed as the ratio of Pn by T, where Pn is the annual net profit and T is the total capital investment. Then there is this concept of payback period. Payback period is the time needed to recoup the initial investment from the net cash flows. The investment generate. So PBP is equal to delta divided by Pn plus D, where Pn is the annual net profit, D is the annual depreciation, and delta is the initial investment. And net present value, NPV. So NPV is the sum of the present values of incoming and outgoing cash flows over a period of time, which provides a method for evaluating and comparing project with cash flows spread over many years. So NPV is computed as a summation of I is equal to 1 to n Ci minus 1 plus r to the power I minus C naught, where Ci is the net cash flow during the period, R is the discount rate, C naught is the initial investment, and N is the number of periods. So discounted cash flow rate of return, or what we call it as internal rate of return, IRR, it is the discount rate in which the NPV, okay, which is the net present value of the cash flows, which are both positive and negative, from a project or an investment equal to 0. So 0 is equal to sigma I is equal to 1 to n Ci minus 1 plus r power I minus C naught. So this equation, of course, you can see you can't solve it as it is. This is an implicit expression. This equation is solved typically by trial and error to find the R, which is the internal rate of return. For a project to be acceptable, its internal rate of return should be greater than the cost of the capital. So now let us look at another concept called eco-efficiency. So eco-efficiency comes in is when if there is the creation of more value with less environmental impact by minimizing the quantity of the material used or a product or service to decrease the waste and resource depletion, lowering the amount of energy required for production, process to save resources and reduce greenhouse gas values, minimizing the use and release harmful substances to protect environment and human health, designing products that can be easily recycled, thus extending the life cycle of materials, reducing the need of virgin resources, prioritizing renewable resources over finite ones to ensure sustainable supply of materials and energy, creating longer lasting products to reduce the frequency of replacement, which in turn decreases the resource consumption and waste. And finally, shifting the focus from the product manufacturing to provide services which often require fewer resources and result in lower environmental impact. So, these strategies are instrumental for companies or industries in aiming to align with sustainable development goals while still maintaining improving profitability and market competitiveness. So, now let us define what we call it as something known as intensity. So, what is the difference between eco-efficiency emphasizes the reduction of the intensity of various kind of resources. So, intensity, how do we now quantify? As the interaction between the system and the environment, interaction between the system and the economy. So, again consider an example. Fine. Um, so, a factory emits 200 tons per year CO2 and uses 10,000 liter per year of water to produce 50,000 units of a bearing, which has an annual profit of $10,000. Determine its eco-efficiency by using a more efficient furnace. CO2 emissions can be decreased by 15% for a 5% decrease in the profit. Water use and the production rates remain unchanged. What will be the coefficiency of the furnace if this furnace is installed? So, again, so you are making 200 tons by using 52,000. So, you are making 200, you are generating 200 tons of CO2 by making 50 to 50,000 units of bearing. So, the efficiency would be 200 divided by 50,000, which is 4 into 10 power minus 3 fine tons of CO2 per unit. And what is water intensity in this case? It is 10,000 liter of water is used for making 50,000 units of product. So, it would be 10 times 10,000 divided by 50,000, which is like 0.2 liters of water H2O per unit. That is the corresponding CO2 intensity and the water intensity. So, now look at what is the, when we have higher efficiency of furnace, what is the amount of emission. So, your efficiency is now 85% and it becomes 170 tons per year. And the profit in that context would be okay. So, it 0.95 times 10,000 would be 9,500. So, what is the steps what we need to follow? A holistic engineering design that includes sustainable practices. So, what is the worst case? You forget the environment, then what we do? We just maximize the profit. This is what we have done initially by means of pinch analysis and so on and so forth. We just try to maximize the profit and forgotten the environment. Now, when you bring environment as a constraint, so you can maximize the profit and also satisfy certain environmental constraints. So, then we can have include local impact as an objective. Again, in that context, you maximize the profit, minimize the local environmental impact. Then the next is life cycle impact. You can include as an objective. It would then you will have to maximize the profit, then minimize the life cycle environmental impact. And the next is respecting natural resources and objectives. So, that is the final goal wherein you not wherein you while we maximize the profit, we minimize the overshoot of ecosystem services. So let's look at the below points that explain the evolution of engineering design towards eco-efficiency. Eco-efficiency, techno-economic analysis has traditionally been a primary focus in engineering design, emphasizing economic feasibility. And over the time, sustainability has become a crucial aspect, requiring the consideration of both economic and environmental impacts in the decision-making process. As a result, initially the industry practices largely ignored the environmental impact and aiming solely to maximize the profit. Fine. Once the regulations are introduced, okay, then it's a constraint, then requiring additional to meet. Then the industries would have to meet, or rather, the production unit has to meet certain standards while still prioritizing the profit. And when you have such multiple objectives, how what to do? The process design approach typically involves uh, to incorporate local environmental impacts as an objective along with the profit maximization, leading to the concept of win-win solution. Recently, the scope has been expanded to include life cycle environmental impact of engineering activities aiming to minimize the overall footprint. So, modern engineering designs strives to respect nature's capacity, they're minimizing the overshoot of the ecosystem services and aligning with sustainable development goals. So, what we see here is a Pareto curve that represents the trade-off between two objectives. Fine, one is of course the cost and other is the carbon footprints in terms of tons of CO2 equivalents. And you can have multiple points here. This is the point of minimum cost, fine, and this is the point of maximum uh, cost or minimum carbon footprint. This is the minimum cost, fine, and maximum carbon footprint. Both are not useful. These are the extreme points. And you have the utopia point, which wherein you say that it is the ideal case wherein you have the minimum cost and minimum carbon footprints, which is an unattainable process, and we have the nadir point wherein you have the worst case for both objectives. So, you have the carbon footprint is maximum and the cost is also maximum. And the when we have this box that connects between minimum cost, minimum carbon footprint, and between the other two things, right? For instance, utopia and nadir, it would result in what we call as the operational regime or of the operational constraints. And you can see your typically the cost would typically decrease over time. You have multiple points and you reach a point which we call it as the knee point, fine, and wherein you have kind of got a uh, better trade-off where you have reasonably lesser cost of operation and reasonably lesser carbon footprints. And anything inside this box is feasible, anything outside this box is typically infeasible. Fine. So, let's speak about the energy transformation. So, ecosystems operate as networks of exergy flow, where exergy is a measure of the usable energy within the system. Primary producers like plants, which converts solar exergy to biomass exergy, which is then utilized by heterotrophs across different trophic levels. While some energy used at each trophic level for a life process, ecosystems are efficient in maintaining a low entropy, which means high energy or high exergy or usable energy. So, the energy quality typically increases as it moves up to the trophic level because of the organisms at higher levels use energy more effectively. Hmm. An increase in the entropy are offset to the ecosystems by biological processes such as photosynthesis, which maintains the balance between energy input and dissipation. Ecosystem typically exhibit sustainability through increased networking and cycling efficiency. Waste from one process is used as a source in the other. Ecosystems' resilience to entropy and unsustainability contrast with the industrial system due to this ability to utilize all forms of exergy, including low quality of heat, to adapt through ecological succession, although they can be disrupted by facts such as invasive species. removal from the system. So now let's take an example of an ecosystem that is represented as an energy network. So you have multiple nodes, node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In node 1 out of the 100, so what is happening in node 1? In 100 joule input, okay, 40 joule is wasted, while 60 joule is used by the nodes 2, 3 and 4. 20 plus 30 plus 10 is 60. Fine. Calculate. So, and the question is calculate the overall energy efficiency of the network if node 4 is not available anymore owing to the removal of the species, and what is the new network efficiency. So, the solution, the total input to the network is of course 100 joule, and what is the total useful output is 6 plus 3 plus 8 plus 16 plus 4 plus 1, which is 38 joule. So, the network efficiency eta is 38 divided by 100, which is 38%. Let's say if you remove the node 4, right? So, remove the node 4, fine. So, the total useful network output is 6 plus 3 plus 8 plus 16, while 4 and 1 which is coming from the node 4 is wasted. So, it will become, so you will remove 5, which is 38 minus 5 is 33 by 100, which is the input, which is like 33%. So, now look at a case, a single node in an ecological network has an efficiency of 10% as depicted in this figure A. If a new node is node develops to use the waste from the node 1 and the resulting network is kind of shown as figure B, determine the efficiency of the network 2, network with 2 and again 20 and 200 such nodes. So, in the 2 node framework, okay, fine, for the 2 node framework in figure B, the total efficiency would be 10 plus 9 divided by 100, which is 19%. For one node, the waste is now how much? 0.9 times 100, which is like 90. For two nodes in series, it is again 0.9 times square, right? 0.9 times 0.9, okay, times 100, which is 81. And for three nodes, it would be 0.93, 0.9 cube into 100, which is 72.1. So, the waste, of course, you can see keep on reducing if you have multiple nodes, and for n nodes it would be 0.9 times n power n and times 100. Thus, the efficiency of n nodes in this context would be 1 minus 0.9 time power n, and if you have n is equal to 20, and the efficiency would be 87.8, and n is 200, its efficiency is 99.9%. So, now let us speak about the last two topics, which we call as ecosystem dynamics, industrial symbiosis and circular economy. And what is ecosystem dynamics? Every ecosystem has a dynamics, and this dynamics and so because ecosystems itself are dynamic entities that are not static or in equilibrium with the state, and they are constantly changing because these are systems that has life. Despite of their dynamic nature, ecosystems exhibit resilience to disturbances, maintaining their structure and function up to certain threshold beyond which they collapse to maintain alternative state. Ecological succession represent the changes in species in composition over time. Within an ecosystem, there are two types of succession, primary and secondary. Primary succession occurs on bare substrate without any initial soil, starting from lichens and progressing to complex communities. Secondary succession occurs on a pre-existing soil, such as abandoned agricultural land, and involves early species like grasses that are replaced over time by longer living species. So, now the process of succession can lead to a mature ecosystem that maximizes the use of recycling of resources and energy within the system. And when ecosystem develops, what you would typically see that there would be an increase in complexity and interconnected, which is resulting from efficient utilization of energy and biomass. And what is a mature ecosystem? Mature ecosystems can reach a stage where they become rigid, making them more vulnerable to disturbance that could lead to a loss of accumulated biomass and nutrients and initiate another cycle of succession. So what we here see is always Holling's adaptive cycle. That concept suggests that the ecosystem will go through various of stages. One is of course an exploitation stage, fine. Then there is a conservation stage, then there is a release stage, and eventually a reorganization, which can be linked to the flow and storage of exergy. So you can see eventually you would exploit an ecosystem, then you start eventually conserving it. Fine, this is the, and eventually it started releasing certain output and eventually reorganized to form a particular structure. And what is industrial symbiosis? So industrial symbiosis are designed to replicate the efficiency of natural ecosystem by the waste of one industrial process as a resource to the another, aiming self-sustaining operation that minimizes the waste. This is very similar to this particular case wherein we have ecosystems. When you have interconnected ecosystem, and how do you have more legs? What is the effect of removing a leg, and so on and so forth. So in industrial ecosystem, there are multiple options. One is of course the type 1 with unlimited resource input and unlimited waste, and there is no interaction between industries. And type 2 and type 3 wherein um, there are limited resources or minimum resources are input, and basically minimum to limited waste are output. So this approach is typically characterized by exchange of byproduct between industries, turning waste from one input to another as a value, uh, and thereby reducing the need to extract more processed raw material. That's why you only require minimum resources. So industrial symbiosis promotes a holistic view wherein the network of interconnected industrial systems can work together to optimize resources and thereby reducing minimum environmental impact. So let's look an example here. Consider a coal burning power plant that produces 0.135 kilogram of ash per kilowatt hour of electricity and emits 0.994 kilogram of CO2. The disposal of this ash by landfilling costs zero point 0.1 cents per kilogram. A local cement manufacturer can add the ash to its skin as a resource of minerals and filler. At present, producing 1 kilogram of cement requires 10 gram of minerals, 30 gram of filler. The mineral cost 0.5 cents per kilogram, while the filler costs 0.05 cents per kilogram. The ash contains 2% minerals and the rest is filler. Ash is available to the cement plant without cost, but the transportation cost 0.02 cents per kilogram, which is split equally between two processes. If a symbiosis is established between the power generation and cement manufacturer, how much would be the ash would the cement manufacturer would purchase from the power generation from the power generator per kilogram of the cement produced. So let's consider we have x kg of the ash that can be added to 1 kilogram of cement. The ash contains 0.02 times x, right, x of minerals, and 0.98 times x kilogram of filler. That is what contain 2% minerals. So 2% minerals and 98% fillers. The quantity of the ash that will satisfy 10 gram of the minerals per kilogram of cement could be computed as 0.02 x is equal to 10 gram, which is like 0.01 kilogram. Thereby we could just recompute x, which is like 0.5 kilogram. And now the quantity of the ash that is needed to satisfy 300 gram of the filler, okay, it would be 0.98 times x, which is like 300 gram, right? So which is 0.3, so x would be 0.31 kilogram. The filler is the limited quantity, since if it is more than 0.31 kilogram of ash added per kilogram of the cement, the filler input will be exceed the specified threshold of 300 kilogram per of the cement, and the cement can use 0.31 kilogram of ash per 1 kilogram of the cement produced. So now let us speak kind of briefly touch upon what is a circular economy. Circular economy, so before that we need to understand what is linear economy. The linear economy follows a take, make and dispose model, wherein leading to the lot of waste basically. It represented by a type 1 industrial ecosystem which assumes unlimited resources and create unlimited waste. In circular economy what we do, the materials are reprocessed, reused and recycled. Thereby minimizing the waste. This model is depicted as evolving from type 1 to type 3, with type 3 minimizing resource input and waste input. And performance economy, a typical performance economy focus on the services rather than the product, which promotes the use of products or services. This can facilitate closing the loop of the material or use of companies to retain the ownership and certain ownership and can manage their life cycle of the product. You can see in a way, so you have extracted resource and eventually it go like a cycle. So sometimes you do recycle, sometimes remanufacture, repair, and eventually there is a line of distribution. And resource loss, of course, there may be there, and you can actually add that using industrial symbiosis. With this, I will just conclude the summary of this lecture. So, sustainability and economics. Designing sustainable processes and product requires integrating ecological consideration with economic benefits, leading to the practices like eco-efficiency and industrial symbiosis. And you know what is, we know time value of money in the sustainability recognizes that the financial viability of sustainable process is influenced by the time value of money, requiring the investment to be appraised considering both present and future values. ROI, the rate of investment, PBP, the payback period, NPV, the net present value, DCFR, discounted cash flow rate of return, are other parameters that we have learned. Then we spoke about ecosystem dynamic. Ecosystems are dynamic and resilient with ecological succession. We are showing how they adapt over time, leading to mature and efficient system. Energy and ecosystem. In ecosystems, energy undergo transformations, solar energy to biomass energy, within trophic levels, emphasizing efficient use of cycling of energy. Then we talk about industrial symbiosis. It's a concept that aims to create networks of industrial process that mimics like natural systems where waste from one process to the other can be given as an input or resource or input to the other one. Circular economy, it focuses on the reuse and recycling of material in a continuous loop, thereby minimizing the waste and encouraging the use of products such as services to close the loop of the material use. And finally, what is technological synergy in LCA? It is the incorporation of the interplay between technology and ecology, thereby quantifying just not the environmental impact of the technological system, but also the benefits and services also provided by the ecosystem, thereby getting a synergistic balance. And techno-economic analysis in LCA engages with the economic feasibility alongside the environmental assessment, ensuring that the sustainable solutions are also economically viable. So, with this, I think we come to the conclusion of this lecture and, of course, the conclusion of this course. We hope you had a pleasant journey with us. Okay, in starting from process mass balance to energy balance to the flow sheet design to flow sheet synthesis to heat exchangers to reactors to sustainable designs. Okay, with this we would like to sign off from you, sign off from the course, and wishing you all the best, and let's hope to be in touch. Thank you.